Okay, so now we're going to start with chapter 5, which deals with gases. And what we're going to talk about in this chapter is basically how gases behave and the different laws behind the behavior of gases, and also the theory that is used to explain these behaviors. So, firstly, we're going to talk about gases and their nature. In other words, what are they like? And as you may know, gases are composed of very small particles that are very energetic, always moving in a constant random motion. In fact, most of their motions, if you look at the individual particles, would be straight lines motion unless they come into contact with each other or with the walls of the container. As a result of the behavior of the particles, collectively, the result would be that gases flow readily and they occupy the entire volume of their container. And at this juncture, I want to explain what this term vapor means. You may encounter the term vapor from time to time. A vapor is basically a gas, which is normally a liquid under room temperature and pressure conditions. All right. So, for example, we talk about water vapor and methanol vapor because water and methanol under normal room temperature and pressure conditions are liquids. But when it comes to gases such as oxygen and hydrogen, we do not use the term vapor in associated with those gases because, of course, these gases exist as gases under normal room temperature and pressure conditions. All right? And it turns out that many low molar mass molecular compounds can exist as either gases or as easily vaporizable liquids. All right? So that's one particular property of gases. They tend to have low molar masses. All right? And this slide basically gives you a list of some gases and their typical use in industry. And just to highlight a couple of examples, butane, formula here is C4H10, which is used as a fuel for heating. Helium is used as, of course, lifting gas for balloons. And oxygen, of course, support for combustion and respiration. So those are just some examples of different gases. Okay, so now we're going to look at the theory that is used to explain the behavior of gases, and it's known as the kinetic molecular theory. And according to this theory, basically, as we said before, the gas particles, which may be molecules or atoms, are always in rapid random motion. All right? And what they will do, as I said before, is that they move in a straight line fashion, and this is called translational motion. So based on that observation, we can basically explain why is it, for example, that gases exert pressure on the inner walls of the container that they're in. And that's because the particles are always moving and they're bumping into the walls of the container. And if you can imagine billions of molecules continually hitting the walls of the container, then the net result is that the molecules will exert a pressure on the walls of the container collectively. So that's a reason why gases exerts pressure on the walls of their container. And that's because of the continuous bombardment of billions of molecules on the walls of the container. We can also see the relationship between the pressure and temperature being explained based on this theory, because as we all know, for any gas, if you increase the temperature, the pressure increases. And that makes sense because what happens when you increase the temperature is that you're imparting energy to the gas particles. The gas particles will move faster and would hit the walls of the container more frequently and harder, and therefore that would result in an increase in pressure exerted by the gas on the walls of the container. All right, so that's a summary, and it's a bit more involved. In fact, we're going to get into this in more detail later on, but that's basically a summary of how the kinetic molecular theory works in terms of explaining certain properties exhibited by gases. Okay, so we talked about pressure earlier. We're going to talk about it in more detail. What is pressure? Well, by definition, pressure is a force exerted on an object or on an area per unit area. All right, so people tend to use pressure and force in everyday language as if they mean the same thing. But pressure is one thing and force is another thing, even though they're related to each other. Force simply is a push or pull. So if I'm pushing on something or I'm pulling on something, I'm exerting force on that particular object. Pressure is the force exerted per unit area, right? And therefore, we can express this mathematically as, let me get my pen function here. So we can express pressure as equal to force divided by area, all right? So that's a relationship between pressure, force, and area, all right? And therefore, as a result, the unit of pressure can be expressed in terms of the unit of force and the unit of area according to this equation. Now, let me just say that according to the SI system as stated here, the unit of force is in newtons, and according to the SI system, the unit of area is meters squared. So therefore, if you have newtons up here, meters squared down here, that means that we can express the unit of pressure as being newtons per meter squared. And there's a special name given to this collection of units. It's called the Pascal unit, PA, right? So whenever you see newtons per meter squared, you should understand it's the same thing as the Pascal units. And then, of course, being that the Pascal unit is also an SI unit, we can use prefixes along with the Pascal unit to express larger or smaller values. The most often prefix used in relation to the Pascal is kilo, right? So you can have kilopascal units, right, which is most often used because the Pascal unit is a small unit. There are some other units of pressure as well that is very often used by scientists. You have what is known as the atmosphere unit and also the millimeter mercury unit, which is also the same thing as the torr unit. So the torr unit and the millimeter mercury unit are both one and the same, all right? And it's very easy to convert from one unit to the other because there are established relationships between the different units, which is shown here in this slide, all right? So on this side, in this table here, this little chart right here, we have 1 atmosphere here being said to be equal to all these values expressed in different units. So it turns out that 1 atmosphere is equal to 760 millimeters mercury, which is the same thing as torr units. So 1 atmosphere is equal to 760 torr. And then we have some other units. To be perfectly honest, I don't anticipate us using these units very much, if at all. So I'm just going to skip those and move down to this one right here. 1 atmosphere is also equal to 101,325 newtons per meter squared. And remember, we said that newtons per meter squared is the same thing as the Pascal unit. And then we can go from Pascal to kilopascal by divide by 1,000, because remember, kilo means 1,000. That's what the prefix means. So therefore, 1 atmosphere turns out to be equal to also 101.325 kilopascals, right? So that basically summarizes the relationship between the different units of pressure. So how do we measure pressure? Well, it depends on what you're trying to measure, to be perfectly honest. Now, if you're trying to measure atmospheric pressure, right? And the atmosphere, of course, does exert pressure because the atmosphere is basically a mixture of gases, right? If you recall, we said earlier, I think it was in chapter 2 or chapter 1, that the air that we breathe is mostly nitrogen, about 78% nitrogen. And then oxygen is the next more abundant gas. And then you have some other gases that exist in trace amounts, all right? So we can actually measure the pressure exerted by the atmosphere, which actually varies from day to day depending on the weather conditions, all right? So, and this is where you're going to learn about the origin of the atmosphere unit, right? By definition, the atmosphere unit is the pressure that is exerted by a column of mercury exactly 760 millimeters high. And you're going to see how we come by that, right? So just to remind you of the relationships between the atmosphere, we go back to my pointer function. 1 atmosphere is equal to 760 millimeters mercury, which is equal to 760 torr, which is equal to 101.325 kilopascals. Okay, so I want you to look at this diagram here, which represents what we call the Mercury Barometer, which is on the right. And we're going to compare it to the setup that we have here on the left. In fact, let me deal with the setup on the left firstly. So, what do we have here? We have a trough filled with mercury, all right? And in this trough, we have inserted a tube. Now, this tube is open at this end here. So what that means is that the atmospheric pressure that is acting on the surface outside the surface of the mercury, outside the tube, will be the same as the atmospheric pressure acting on the surface of the mercury inside the tube. So as a result, the mercury level inside the tube will be the same as the mercury level outside the tube. No surprise there, all right? Now compare that to what we have here on the right. Now what do we have on the right? We have a trough filled with mercury, right? And we have a tube here. And this tube, unlike the tube over here, is sealed at one end, right? So the way this is set up in practice is that you have your mercury in your trough right here. Separately, you completely fill the tube with mercury and then you invert it into the trough filled with mercury and you let it stand for a while. And what you'll find is that if the mercury tube or if the tube here is long enough, then the mercury level will fall to a certain height, which is about 760 millimeters, all right? So what does that mean in terms of the relationship between the height of the mercury and the atmospheric pressure? Well, if you consider what is happening inside the tube right here, this mercury column here will exert a pressure at here, at this level here, which is the same level as the liquid outside of the trough. It will exert a pressure here on that level right here, which will be equal to the pressure exerted on the surface of the mercury outside of the tube. So therefore, as a result, what we can say is that there is a relationship between the height of the mercury column above the surface of the liquid and the pressure exerted on the surface of the mercury outside the tube. So therefore, as a result, this basically gave rise to the new unit of millimeters mercury, right? And therefore, the definition of the millimeter mercury unit is that 760 millimeters mercury of pressure would be equal to 1 atmosphere that is exerted on the surface of the mercury outside of the tube, all right? So that's where we get that relationship between the atmosphere unit and the 760 millimeter, or the millimeter mercury unit. Okay, so that's basically how the Mercury Barometer works. All right, so the next slide is a simple question. It says that a Canadian weather report gives the atmospheric pressure as 100.2 kilopascals. So the question is asking, what is the pressure expressed in the torr unit? And this is very simple. It's a simple unit conversion problem. So let me go to my pen function here. So basically, I'm going to start off with 100.2 kilopascals. And I have to multiply by a conversion factor, which relates the kilopascal unit to the torr unit. And going back to the table that I showed you before, you'll see that 760 torr will be equal to 101.325 kilopascals. And then all we have to do from here is our number crunching. So let's do that here. So it's 100.2 times 760 equals that, divided by 101.325. And according to my calculations, when rounded off to 4 sig figs, will give you 751.6 torr. And that's basically how that is done. So, you know, nothing too difficult there. Simple unit conversion. All right? Okay. So we're going to stop here. The next video I'm going to post will deal with another type of instrument that is used to measure the pressure of gases. All right? Okay, until next time.